Hello everyone, so today we will learn about lesson 17. Lesson 17 consists of two chapters, which is chapter 13 and chapter 14. Okay, for chapter 13, we have 13.3. The subtopic is molecular kinetic energy and internal energy. And for chapter 14, we will cover subtopic 14.1, which is first law of thermodynamics. Okay, for the first part, we will discuss about translational kinetic energy of a molecule. Okay, so as you can see here, we have the equation of P equal to 1 over 3 nm v square over v. Okay, we can rearrange this equation. Okay, P equal to 1 over 3. Okay, we take n over v here. Okay, and we have mv square here. Okay, so this equation also can be written as 2 over 3 n over v half mv square. So these 2 and 2 actually can be cancelled out lah. Okay, so from this equation, P equal to 2 over 3 n over v half mv square, we can conclude that P will increase when n over v is increased. Okay, which is n over v is the number of molecules per unit volume. Okay, P also will increase when half mv square is increased. Okay, so half mv square here represent translational kinetic energy of a molecule. Okay, so previously we learned P equal to 2 over 3 n over v half mv squared. We also have learned that PV equal to nkt. Okay, so P from the first equation, we have P equal to 2 over 3 n over v half mv squared. V here can be transferred to the other side. So we have PV equal to 2 over 3 n half mv squared. We compare with PV equal to nkt. Okay, so we will get this equation. Okay, so what happened is we can cancel out and both side. Okay, so 2 over 3, we can bring it to the other side. So the equation will be half mv square equal to 3 over 2 kt, where half mv square is actually our translational kinetic energy. Okay, so from there, we know that translational kinetic energy is equal to half mv square, or translational kinetic energy is equal to 3 over 2 kt. Okay, or this equation can be written as translational kinetic energy equal to 3 over 2 r over na times t. This equation also called as average kinetic energy per molecule. Okay, it only depends on temperature for all types of molecule. Okay, so from here, KTR means translational kinetic energy of a molecule. T is the absolute temperature and measured in Kelvin. While K is the Boltzmann constant, 1.38 times 10 power negative 23 joule per Kelvin, and R is the molar gas constant, which is 8.31 joule per Kelvin per mole. Na is the Avogadro constant, 6.02 times 10 power of 23 per mole.
We study about degrees of freedom. The number of directions in which a particle can move freely is defined as its degree of freedom, or the number of independent coordinates required to specify completely the position and orientation of a particle in space is defined as its degree of freedom. Degrees of freedom are of three types. They are 1. Degrees of freedom of translational motion, Ft. 2. Degrees of freedom of rotational motion, Fr. 3. Degrees of freedom of vibration motion, Fv. Degrees of freedom of translational motion, Ft. These are due to translational motion of molecules. Maximum number of translational degrees of freedom is 3, irrespective of that the molecule may be monatomic or polyatomic, linear or nonlinear. These are present at ordinary temperature. Degrees of freedom of rotational motion, Fr. These are due to rotational motion of a molecule about an axis passing through the center of mass of the molecule. Their number depends upon the structure of molecule. These are also present at ordinary temperatures. Degrees of freedom of vibrational motion, Fv. These are due to the vibrational motion of molecule about its equilibrium position. The number depends upon the structure of the molecules. These are produced only at high temperatures. Degrees of freedom for monatomic gas. A monatomic gas molecule can move linearly in any direction along 3 coordinate axes. Hence, its degrees of freedom is Ft is equal to 3. Examples: molecules of noble gases like helium, neon, argon, etc. Diatomic gas. The center of mass of 2 atoms is free to move along 3 coordinate axes. Hence, its translational degrees of freedom is Ft is equal to 3. The molecules, if these gases can rotate about a perpendicular axis passing through their center of mass in 2 directions. Hence, its degree of freedom of rotating motion is Fr is equal to 2. Therefore, total degree of freedom F is equal to Ft plus Fr is equal to 3 plus 2 is equal to 5. A triatomic or polyatomic gas, nonlinear. Degrees of freedom of translational motion, Ft is equal to 3, and degrees of freedom of rotational motion, Fr is equal to 3. Therefore, total degree of freedom F is equal to Ft plus Fr is equal to 3 plus 3 is equal to 6. Note: in general, degrees of freedom can be determined as F is equal to 3n minus b. N number of coordinates required to specify a thermodynamic system, and b number of constraints.
Okay, now we will look at degree of freedom. Okay, what is degree of freedom? It is defined as the number of independent ways in which an atom or molecule can absorb or release or store the energy. Number of independent ways of an atom or molecule can absorb or release or store energy. So we have 3 types of gas, which is the first one is monoatomic gas. So number of degree of freedom for monoatomic gas is 3. Okay, 3 direction of translational motion is x axis or x component, y component, and x and x, y and z component. Okay, second one is diatomic gas. Okay, diatomic gas, the number of degrees of freedom is 5. Okay, where the translational kinetic energy degree of freedom is 3, while the rotational kinetic energy is 2. Degree of freedom is 2. Okay, polyatomic gases such as H2O, CO2 and H3, the number of degree of freedom is 6, where translational kinetic energy, the degree of freedom is 3, and rotational kinetic energy, the degree of freedom is 3 also. So the total number for polyatomic gases, number of degree of freedom is 6. Okay, so now we'll discuss about internal energy. Internal energy is the sum of total kinetic energy and total potential energy of the gas molecules. Okay, sum of. So it is K plus U. But in ideal gas, the intermolecular forces are assumed to be negligible. Thus, the potential energy of the molecules can be neglected. So, U can be neglected. Okay, thus for n molecules, internal energy is equal to number of molecules times total kinetic energy, where total kinetic energy here is F over 2 kT, where F is our degree of freedom. Okay, so the internal energy U equal to N times F over 2 kT, or it also can be written as F over 2 N kT or F over 2 N RT. Okay, so now we look at principle of equipartition of energy. It states the mean kinetic energy of every degree of freedom of a molecule is half kT. So for each degree of freedom, the average kinetic energy is half kT. Okay, so this table represents the number or degree of freedom. Okay, for monoatomic gas, for translational is 3, rotational is 0, so the total is 3. Okay, while the kinetic energy per molecule for monoatomic gas per molecule means average, so 3 over 2 kT. Total kinetic energy per molecule, this one is same with this one, but this one is internal energy for all molecules, so we must time with the number of molecules. Same goes with diatomic and polyatomic. So the equation for total kinetic energy per molecule depends on degree of freedom. So for monoatomic, the degree of freedom is 3, so it will be 3 over 2 kT. For diatomic, the degree of freedom is 5, so 5 over 2 kT. For polyatomic, the degree of freedom is 6, so it will be 6 over 2 kT or 3 kT. Okay, you can try this example. Okay, let's continue with chapter 14, Thermodynamics. For subtopic 14.1, okay, what is thermodynamics? Thermodynamics is the study of relationship between involving heat, mechanical work and other aspect of energy and energy transfer of the system. So, what is first law of thermodynamics, or the short form is FLOT? Okay, it states that the heat Q supplied to a system is equal to the increase in the internal energy of the system plus the work done by the system on its surrounding, or it can be represented by Q equal to delta U plus W, where Q is the quantity of heat, W is the work done, delta U is the internal energy. So this is the equation for the internal energy. Okay, change in internal energy. So when we said it is the change, so it must be U final minus U initial. So previously we have learned about the equation for internal energy, which is F over 2 nRT. So for U final, F over 2 nRT final minus F over 2 nRT initial. Okay, so this is the first law of thermodynamics. Okay. When Q is added to a system, the temperature of the gas decrease. So Q added, T increase, causing the internal energy to increase. So delta U also increase by an amount of delta U joule. At the same time, when its temperature is increases, the volume increases too. So when T is increased, V also increase. When the volume of the gas increase, work is done by the gas. So when volume increase, work is done. Okay, so you can see in the diagram. So Q added, what happened? Q added, V will increase. So when V increase, work is done by the system. Okay. So from the first law of thermodynamics, Q equal to delta U plus W. So what is the sign convention for Q, W and delta U? Okay, so Q is positive, means heat is flow into the system. We add some heat into the system. When Q is negative, the heat is flow out of the system. Positive in, negative out. Okay, this one is for Q. Okay, for delta U, positive value means T is increased or internal energy is increased. Delta U negative means internal energy is decreased or T is decreased. So for delta U, positive means T increase, negative means T decrease. So when T increase, delta U also increase. When T decrease, delta U also decrease. Okay, so now for work. Work positive means work is done by the system or the gas will expand. Work negative means work is done on the system. So for W, positive means by, negative means on. By means expand. On means compress. Okay. So the internal energy depends on temperature. As you can see, delta U is equal to F over 2 and KT, right? So delta U depends on temperature. Sorry, U depends on temperature. Okay, if the initial and final temperature is the same, so T final and T initial same, so delta U equal to 0. Okay, the internal energy does not depend on pressure and volume because it only depends on temperature. The change in internal energy of a system during any thermodynamic process is independent of path. For example, a thermodynamic system goes from state 1 to state 2 as shown in figure 1 to 2. Okay. Okay, for example for work done by the systems and work done on the system. So initially, okay, this is the initial volume. Okay, expansion means the volume will increase. Motion of the piston is upward. Compression means the motion of the piston is downward or the volume will decrease. Okay, so you can try this exercise. Thank you.